Hey GED students, it's GED question of the daytime, and I just wanted to dig a little bit deeper into the concept of equivalent fractions. Students who struggle with fractions usually don't get this concept, and that is that fractions that look very different. They have different numerators, they have different denominators. They could have really small numbers on the top and the bottom, they could have giant numbers on the top and the bottom, could still be equivalent, meaning completely and totally equal to each other, meaning the exact same number in disguise. And so what I mean by equivalent is equal. Now, it's so interesting to me because students just don't see how that could be true. They look at these four fractions, they're like, none of them look equivalent to me. They have different numbers. But remember that a fraction is not the individual numbers. A fraction is a relationship. It's a relationship between numerator and denominator. And as it turns out, fractions that look very, very, very different can have the same basic relationship. Okay, so there are a couple of different ways to prove equivalence. We've talked about it in the last two videos, but because I have so many fractions to deal with this time, instead of doing the cross products thing like we did in the last video, go check that out if you want to see that, but I'm just going to reduce all these fractions because I know that reducing a fraction to lowest terms brings it back down and boils it down to that basic relationship between the top and the bottom. Okay. And so if all these fractions are equivalent, if they're equivalent, they will reduce to the same thing. And I say that again, equivalent fractions reduce to be identical. Okay, so let's check it out. So when I go to reduce, I am always flipping through my divisibility tricks, looking for patterns that help me to see common factors. Right here with A, I am cheering because I notice this double repeated digit thing. That's two twos. That's two fives. I know a times tables that works like that, at least in the double digit numbers. That's the 11s. So this guy's screaming at me that it has 11s. I'm going to divide out those 11s that it has in common. Of course, there are two 11s in 22. That's why it's made of twos. You ever list out the 11 times tables? They are easy. And there are 5 11s in 55. So this fraction is most basic relationship. The relationship between the fraction 22 over 55 is for every 2 things in the numerator, there are 5 things in the denominator. It reduces to 2/5 because that is the basic relationship of 22 over 55. And so 22 over 55 is exactly and totally equivalent to 2/5. Let's try another one. 6 over 15 also has some common factors. These ones stump students a lot, but let's just think about 6. 6 is made of a 2 and a 3. There's only 2 possibilities here to divide 6 by 2 or 3, or I suppose 6, but yeah, sorry. There's only 2 prime suspects, 2 or 3. That being said, I happen to know 15 is on the 3 times tables, and so I see that they have a common factor of 3. I'll divide the common factor out of both the top and the bottom. So 6 divided by 3 is 2. The 2 will be left. 15 divided by 3 is 5. And look what I see. The fraction 6/15 has that same basic relationship that for every 2 things on the top, there are 5 things on the bottom. I'm even going to draw a picture for you. For every 2 things on the top, there are 5 things on the bottom. So that's 2/5. But 6/15 is just that same relationship 3 times. For every 2 things on the top, 5 on the bottom. For every 2 on the top, 5 on the bottom. For every 2 on the top, 5 on the bottom. So that 6 over 15 is the same. Oh, I didn't even write 2 over 5. I wrote 2 over 2, even though I keep saying 2 over 5. Y'all, you better watch me. This is what I get for making videos in the morning. But for every 2 things on the top, there are 5 things on the bottom. The basic relationship here is 2 to 5. Now let's try with 14 over 30. Now, this one might be a little more challenging for you to reduce, but one thing I notice is that these fractions are both even, and I know all even numbers are divisible by 2. Again, let me clarify. the numerator and the denominator are both even. And so I know I could pull a common factor of 2 out of both of them. So 14 divided by 2 is 7. 30 divided by 2 is 15. Now, this one might trick you a little bit. Is there anything else I can divide by? But just by thinking of what 15 is made of, 15 is composed of 3 and 5, 3 times 5. Those are the factors, prime factors there of 15. I can't divide 7 by 3. I can't divide 7 by 5. I'm not going to find anything else in common. The only thing these things have in common is 1. So 1 and done. And so I can see that this fraction has a different relationship. This fraction has the relationship that for every 7 things on top, there are 15 things on the bottom. Okay, so I highly suspect C is the right answer, but let's just be good mathematicians and check all our answers, because it is possible for us to make mistakes. So let's try D2 just to verify that it is this equivalent. It is the same as the others. So 10 out of 25, I see a common factor screaming at me here. These numbers end in 0 and 5. They must be divisible by 5. 10 divided by 5 is 2. 25 divided by 5 is 5. And again, I see that same basic relationship. For every 2 things on the top, there are 5 things on the bottom. And I would see that if I did the fraction 10 out of 25. If I ended up with 10 dots. See how I have 10 dots on the top? But I group them by 2s, because for every 10 on the top, I have 5 on the bottom. And I'm just going to show to you that this relationship 2 over 5 is repeated when I get up to 10 out of 25. So you can see this is 2, 4, 6, 8, 10 dots up top. And counting by 5s on the bottom, 5, 10, 15, 20, 25 dots on the bottom. And it's just that relationship of 2 out of 5 repeated over and over again. Okay, so wonderful. 3 of these 4 fractions come to 2/5. And I was looking for the fraction that was not equivalent to the other 3. So obviously it was C, just like I suspected. Great. If you have any questions about this or any other GED math concept, be sure to drop it in the comments, and I'll do my very best to answer it.